right, so this is the limit comparison, and we use this one when we have issues with this one. So if we go straight for this one, we already know our a sub n would be 2 over square root of n plus 2. And you would pick for your b sub n by now 2 over the square root of n, which is 2 over n to the 1/2. And since we have a p that is less than or equal to 1, we would say it's divergent. So then you go, okay, well, if it's divergent, then all I have to do is put greater than. But you can't. See, the plus 2 is something we can't get rid of. So we now move off to the limit comparison. And what the limit comparison states is this. You have two series A and B with positive terms. And so if the limit of a(n) over bn is equal to c, where c is bigger than 0, so you just have to take the limit of a sub n over b sub n and it equals some number bigger than 0, then either both series will converge or both will diverge. So we can show that this one is divergent. So we can already go, well, the sum of n equals 1 to infinity of 2 over n to the 1/2 is divergent because p is less than or equal to 1. All right, so now we've shown that. So now if we can show that the limit of as n approaches infinity of a sub n over b sub n is equal to c, then because our b sub n is divergent, our a sub n also has to be divergent. So that's what we're going for. We're trying to show, this is not shown, show it's divergent. Good enough. All right, divergent. All right, so what we do is we take our limit of a sub n over b sub n, and I've already got that here, and we rewrite it. So limit as n approaches infinity of a sub n over b sub n, and so that would be the limit as n approaches infinity. And the way you write it is just like any other fractions. When you're dividing by a fraction, you take the reciprocal. So this would really just be rad n over 2. Let me move it down a bit. All right, we're just trying to show that this is some number that's bigger than 0. So the 2's would cancel, giving us rad n over rad n plus 2. And we treat these just like our normal fractions. So we're going to divide everything by radical n. So we would get 1 plus 2 over radical n. And this goes off to infinity. I mean, not infinity. As it goes to infinity, it goes to 0. All right, so we end up with 1. And 1 is bigger than 0. So that's what we're saying. We're trying to find some value c, where c is bigger than 0. Check. So, by the limit comparison test, the sum from n equals 1 to infinity of 2 over rad n plus 2 diverges. See, we've already shown this. Oh, that looks horrible. I don't know what that was. It wasn't a star. There we go. And we showed this. And so we just met both of them. So it's saying that, again, if our limit equals c, if one of these converges, they both converge. If one of them diverges, they both diverge. That's what this is saying. So because this series diverges and our limit is equal to 1, they both diverge. So where this is coming from is, if you just think about it, if you have a limit for a sub n over b sub n that is equal to some value c, then that c is going to be between m and some other value m. It's actually less than, right? That we have some limit then. It's max, so our c. So that means these two have to be between two numbers as well. The smallest number in that series, right? And then all the way up, it's going to be have a limit of c. So it can't go over that. Now, if we multiply everything by b sub n, we end up with this. And so what we're doing now is basically applying both of these. And so you can see now that a sub n is less than b sub n. And a sub n is bigger than b sub n with some other m. So if b sub n converges, a sub n converges. And if b sub n diverges, a sub n diverges. That's what we're using these two for. So it's just basically applying these two into a limit formula. All right, so let's try it again. So our a sub n here would be 1 over n square root of n squared minus 1. And our b sub n is equal to, and if you just use the n's, right, that would be n squared with a square root, which would be n and n, 1 over n squared. And what do you think this would do? As we take b sub n to infinity, this is going to converge because our p is greater than 1. So we're looking at this converging. So if this one converges, this one should converge as long as our limit approaches some number that's bigger than 0. So we have the limit as n approaches infinity of our a sub n times n squared over 1. And the reason we can't just say, oh, remember with this we're supposed to do less than, but because we have a minus 1, it messes stuff up. So we use this instead. Okay, so let me move it down a bit. All right, so you can see right away that those n's cancel. And so we have limit of n approaches infinity of n over the square root of n squared minus 1. And then we do that same thing again, where we're going to divide everything by n. So I'm going to take this one a little bit slower. This would be n over n. And then since we have a square root, we're really putting in there an n squared. Because if you take n square root n, you would get n. So that's all that is. All right. That cancels, and we end up with the limit as n approaches infinity of 1 over the square root of 1 minus 1 over n squared. That goes to 0. And again, we get 1, which is greater than 0. So by the limit comparison test, the sum from n equals 2 to infinity of 1 over n square root of n squared minus 1 converges. So again, the same basic idea. This limit is bigger than 1. So since this converges, that one converges. So they both converge, or they both diverge as long as that limit is bigger than 1. Or sorry, bigger than 0.